If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The asteroid belt, a cosmic crossroads. Imagine a vast region of space, a celestial graveyard teeming with fragments of rock and metal, remnants of the chaotic forces that birthed the solar system. This is the asteroid belt, a band of objects suspended between the orbits of Mars and Jupiter. It stretches across a staggering 329 to 478 million kilometers from the Sun, a cosmic no man's land that marks the boundary between the inner rocky planets and the outer gas giants. Yet, despite its location and name, the asteroid belt is far from an impenetrable wall of debris. It is instead a dynamic and mysterious region, whose secrets could unlock the story of the solar system's creation and even the origins of life itself. Why does the asteroid belt exist, and what can it tell us about the cosmos? To answer these questions, we must first understand what this region is and why it occupies such a unique position. Unlike the densely packed asteroid fields of science fiction, the real asteroid belt is an expansive and sparse region, where vast distances separate individual asteroids. If all its mass were combined, it would form an object only about 4% the size of Earth's moon. Yet, its significance far outweighs its mass. The belt is a reservoir of ancient materials, leftovers from the early days of the solar system when dust and gas coalesced into planets. The story of the asteroid belt begins approximately 4.6 billion years ago, during the formation of our solar system. In the swirling protoplanetary disk of gas and dust, particles collided and clumped together, forming planetesimals. These building blocks of planets either grew into the worlds we know today or were scattered, absorbed, or destroyed. But not all planetesimals completed this journey. Between Mars and Jupiter, a delicate balance was disrupted. The gravitational influence of Jupiter, the solar system's giant, prevented the material in this region from forming a single planet. Instead, the fragments remained in limbo, evolving into the collection of objects we now call the asteroid belt. What kinds of objects populate this mysterious region? The belt is home to a diverse array of asteroids, ranging from small, irregularly shaped rocks to large, spherical bodies like Ceres, the belt's only dwarf planet. Asteroids are categorized by their composition. Some are rich in carbon, while others contain silicates or metals like nickel and iron. This diversity reflects the conditions and locations in which they formed, with some originating closer to the Sun and others further away. Intriguingly, the asteroid belt is not just a relic of the past. It is a dynamic system where collisions, migrations, and interactions continually reshape its landscape. Asteroids occasionally escape the belt, propelled by gravitational interactions or collisions, becoming near-Earth asteroids that cross our planet's orbit. These wanderers are both a potential threat and a source of fascination, offering insights into the primordial materials that seeded life on Earth. The asteroid belt also serves as a bridge between the inner and outer solar system, acting as a conveyor of material. It may have played a crucial role in delivering water and organic molecules to Earth, sparking the conditions necessary for life. Yet, it remains a frontier of unanswered questions. How did water-bearing asteroids come to exist? Could similar processes be occurring in other star systems? And what mysteries lie hidden in its dark, untouched regions? To uncover these secrets, scientists have launched missions to explore the belt directly. NASA's Dawn spacecraft, for example, studied the two largest bodies in the belt, Vesta and Ceres, revealing their unique compositions and histories. Vesta, with its volcanic surface, offers a glimpse into the early differentiation of planetary bodies, while Ceres, with its potential subsurface ocean, raises tantalizing possibilities about habitability. These missions are just the beginning of our journey into the asteroid belt's mysteries. As we delve deeper into its secrets, the asteroid belt emerges as more than a collection of rocks. It is a cosmic crossroads, a place where the forces of gravity, chemistry, and time converge. Its story is intertwined with the broader narrative of the solar system, from its chaotic beginnings to its present form. By studying the belt, we not only uncover the history of our own celestial neighborhood, but also gain a deeper understanding of the processes that shape planetary systems throughout the universe. Formation of the belt. A failed planet or cosmic evolution. When we gaze upon the asteroid belt, it's tempting to imagine it as the remnants of a celestial body that almost was a failed planet that never completed its formation. For centuries, this idea captured the imagination of astronomers, painting a dramatic picture of a shattered world scattered across space. But as our understanding of planetary science evolved, a more nuanced narrative emerged, one that highlights the intricate dance of gravity, chemistry, and time that shaped this region. How did this vast expanse of rocky debris come to be, and why does it remain a fragmented graveyard instead of a fully formed planet? To answer this, we must rewind to the solar system's earliest days, a time of chaos and creation when the sun was surrounded by a swirling protoplanetary disk. This disk, made up of gas, dust, and ice, was the raw material from which planets formed. Within this turbulent environment, particles collided and stuck together, gradually building larger bodies known as planetesimals. In most parts of the solar system, these planetesimals merged into protoplanets, the seeds of the worlds we know today. But in the region now occupied by the asteroid belt, a powerful influence intervened: Jupiter. The immense gravitational pull of the gas giant disrupted the orbits of planetesimals, creating a region of instability where collisions became more destructive than constructive. Instead of coalescing into a planet, the material was fragmented, creating the diverse population of asteroids we see today. Yet, the story doesn't end there. The asteroid belt, as we know, it is a shadow of its former self. Models suggest that the early solar system contained far more material in this region, enough to form a planet comparable in size to Earth. Over billions of years, much of this material was lost, either ejected from the solar system by gravitational interactions or pulled into the sun and other planets. What remains is a fraction of the original mass, preserved as a testament to the forces that shaped the solar system. What, then, of the idea that the asteroid belt represents the remnants of a planet that was destroyed in a cataclysmic event? This theory, while once popular, has largely been debunked. The composition and distribution of asteroids do not support the notion of a single, unified origin. Instead, the diversity of asteroids, ranging from carbon-rich C-types to metallic M-types and silicate-heavy S-types, suggests they formed in different locations and under varying conditions. Their current positions are the result of billions of years of gravitational reshuffling and collisions. One of the most intriguing aspects of the asteroid belt is its role as a time capsule. The asteroids that populate this region are among the most ancient objects in the solar system, preserving materials that date back to its very beginnings. By studying these objects, scientists can peer into the past, uncovering clues about the conditions and processes that shaped the planets. The belt's composition also hints at its complex history, including migrations of planets and the influence of chaotic resonances. A pivotal piece of this puzzle is the concept of the snow line, a boundary in the early solar system where temperatures were low enough for volatile compounds like water and ammonia to condense into ice. The asteroid belt straddles this line, and its composition reflects this duality. Some asteroids, especially those closer to the sun, are rocky and metal-rich, while those farther out contain significant amounts of ice and carbonaceous material. This distribution provides critical insights into the thermal and chemical gradients of the protoplanetary disk. But what does this mean for the belt's significance today? Beyond its historical importance, the asteroid belt serves as a natural laboratory for studying planetary formation. It offers a unique opportunity to test theories and refine models, shedding light on the processes that shape not only our solar system, but also the countless others scattered across the universe. By understanding the belt, we can better grasp the factors that determine why some regions give rise to planets while others remain as debris. The asteroid belt also raises profound questions about the nature of cosmic evolution. What if Jupiter hadn't formed where it did? Could a planet have emerged in its place, altering the course of the solar system's history? And what role did the belt play in shaping the conditions for life on Earth? These questions remind us that the asteroid belt is more than a static collection of rocks. It is a dynamic, evolving system, deeply connected to the broader narrative of the cosmos. As we uncover the secrets of the belt's formation, we are reminded of the delicate interplay of forces that govern the universe. The asteroid belt stands as a monument to these forces, a region of space where the line between creation and destruction is finely drawn. It is both a remnant of the past and a key to the future, holding answers to questions we have yet to ask. Hidden treasures, metal and mineral wealth. Beneath the surface of the asteroids lies an untapped wealth that could redefine humanity's future. The asteroid belt is not just a repository of ancient materials. It is a treasure trove of metals and minerals, offering resources that could fuel industries, power technologies, and even sustain life beyond Earth. But what exactly is hidden within these celestial bodies, and how might we unlock their potential? To understand the value of the asteroid belt, we must first consider the composition of its inhabitants. Asteroids are categorized into three main types based on their mineral makeup: C-type, carbonaceous; S-type, silicaceous; and M-type, metallic. Each type holds a distinct set of resources, reflecting the environments in which they formed and their unique histories. C-type asteroids are the most common, accounting for about 75% of known asteroids. Rich in carbon, they also contain water, ammonia, and organic compounds. These materials are of immense scientific interest, offering clues about the origins of life. More practically, they could serve as sources of water for future space missions, providing the essential ingredients for drinking, agriculture, and even rocket fuel through electrolysis. S-type asteroids, comprising about 17% of the belt's population, are dominated by silicate minerals and metallic compounds. These asteroids are particularly rich in iron, nickel, and magnesium, making them valuable for construction and manufacturing. M-type asteroids, though rarer, are pure treasure chests of metals, containing vast quantities of iron, nickel, cobalt, and even precious metals like gold and platinum. A single M-type asteroid, just a few kilometers wide, could hold more metal than has been mined in all of human history. The potential economic value of these resources is staggering. Studies estimate that the mineral wealth of the asteroid belt could amount to quadrillions of dollars, dwarfing the global GDP many times over. Yet, this wealth is not just a matter of monetary value. It represents an opportunity to revolutionize our approach to resource scarcity, shifting the focus from Earth's finite reserves to the virtually limitless expanse of space. But how realistic is the prospect of mining the asteroid belt? The concept, once relegated to the realm of science fiction, is rapidly becoming a scientific and engineering challenge. Advances in robotics, artificial intelligence, and propulsion systems are bringing asteroid mining closer to reality. Companies and space agencies are already exploring the feasibility of extracting resources from near-Earth asteroids, which serve as stepping stones to the belt itself. One of the key challenges is the sheer distance involved. The asteroid belt lies between 2.2 and 3.2 astronomical units, AU, from the Sun, far beyond the reach of current mining operations. Transporting materials back to Earth would be prohibitively expensive under current technologies. However, the resources could be used in space, supporting the construction of habitats, spacecraft, and even entire industries in orbit. By leveraging in-situ resource utilization, ISRU, humanity could establish a self-sustaining presence in space, reducing our reliance on Earth-based resources. Another critical factor is the identification of target asteroids. Not all asteroids are created equal, and selecting the right ones for mining requires careful analysis. Space missions like NASA's OSIRIS-RX and Japan's Hayabusa 2 have already begun sampling near-Earth asteroids, providing valuable data about their composition and structure. Future missions to the asteroid belt will likely include similar reconnaissance efforts, paving the way for large-scale mining operations. However, the prospect of asteroid mining also raises important ethical and legal questions. Who owns the resources of the asteroid belt? Should they be treated as a global commons, or will private companies and nations stake claims? The Outer Space Treaty of 1967, which forms the basis of international space law, prohibits sovereign claims over celestial bodies, but leaves room for interpretation when it comes to resource extraction. As interest in asteroid mining grows, the need for clear regulations and cooperative frameworks becomes increasingly urgent. Beyond the practical challenges, The pursuit of asteroid mining represents a profound shift in how humanity views space. No longer merely a frontier for exploration, space is becoming an extension of human enterprise. This shift has the potential to drive technological innovation, economic growth, and even social change, as the resources of the asteroid belt enable new possibilities for sustainable development and equitable access to wealth. What would it mean for humanity to harness the riches of the asteroid belt? On one level, it could address some of our most pressing challenges, from resource scarcity to environmental degradation. On another, it could open the door to a future where humanity is no longer confined to a single planet. The asteroid belt, with its vast reserves of metal and mineral wealth, could serve as the foundation for a spacefaring civilization, providing the raw materials needed to build habitats, ships, and infrastructure in the solar system and beyond. As we stand on the brink of this new era, the asteroid belt reminds us of the boundless opportunities that await in space. It challenges us to think big, to innovate, and to work together to unlock its potential. The treasures hidden within its depths are not just resources. They are stepping stones to the stars, inviting us to expand our horizons and redefine what is possible. Ceres, the dwarf planet among giants. Amid the countless asteroids that populate the belt lies a singular world that stands apart, a dwarf planet named Ceres. At nearly 940 kilometers in diameter, Ceres accounts for approximately one-third of the asteroid belt's total mass, making it the largest object in this vast region. But size alone isn't what sets Ceres apart. This enigmatic world, with its intriguing surface features and hidden secrets, offers tantalizing clues about the potential for life and water beyond Earth. Ceres was discovered in 1801 by Giuseppe Piazzi, who initially believed it to be a planet. However, as more objects were discovered in the same region, Ceres was reclassified as an asteroid, and later, in 2006, it gained the distinction of being a dwarf planet. Despite its historical significance, much about Ceres remained a mystery until NASA's Dawn spacecraft arrived in 2015, providing humanity with its first close-up views of this enigmatic world. What makes Ceres so intriguing is its unique combination of characteristics. Unlike most asteroids, which are irregularly shaped fragments, Ceres is spherical, its shape molded by gravity. Its surface is marked by craters, ridges, and mysterious bright spots that have puzzled scientists since their discovery. These bright regions, found in craters like a crater, are composed of sodium carbonate, a type of salt that forms in the presence of water. Their presence suggests that Ceres may have had, or still has, subsurface liquid reservoirs. Could there be water on Ceres? The evidence is compelling. The dwarf planet is thought to have a thick crust of ice, and observations suggest that water vapor occasionally escapes into space, likely through sublimation or cryovolcanism. This raises the possibility that Ceres harbors a subsurface ocean, akin to those believed to exist on icy moons like Europa and Enceladus. If confirmed, such an ocean could provide a stable environment for microbial life, making Ceres a key target in the search for extraterrestrial habitability. Adding to its intrigue is the potential for organic molecules on its surface. Dawn's instruments detected traces of organic material in certain regions, hinting at complex chemical processes that could contribute to life's building blocks. While these findings do not confirm the presence of life, they strengthen the case for Ceres as a world of scientific interest, where the boundary between the chemical and biological realms may be explored. Ceres also offers insights into the formation and evolution of the solar system. As a protoplanet that never fully developed, it preserves materials and structures from its early history. By studying Ceres, scientists can reconstruct the conditions that prevailed in the asteroid belt during the solar system's infancy. For example, its icy composition suggests that it formed beyond the snow line, where volatile compounds could condense. Over time, gravitational interactions likely moved it inward to its current position, providing a window into the migrations of planetary bodies. But Ceres is not merely a relic of the past. It also holds promise for the future. Its resources, particularly its water ice, could prove invaluable for space exploration. Water can be used not only for life support, but also as a source of hydrogen and oxygen for rocket fuel. By establishing a presence on Ceres, humanity could create a supply depot for missions deeper into the solar system, turning this dwarf planet into a stepping stone to the outer planets and beyond. As we consider the potential of Ceres, it's important to remember the challenges it presents. Any attempt to explore its subsurface or harness its resources will require advanced technologies and careful planning. The thin layer of water vapor detected by dawn suggests that accessing Ceres' buried treasures may be more complex than drilling into a frozen surface. Additionally, international cooperation and legal frameworks will be essential to ensure that the exploration of Ceres and its resources is conducted responsibly and sustainably. Despite these challenges, the allure of Ceres continues to grow. It stands as a testament to the diversity and complexity of the asteroid belt, a world that defies simple classification. It is an asteroid, a dwarf planet, a potential water world, and a scientific laboratory rolled into one. By unlocking its secrets, we not only advance our understanding of the asteroid belt, but also deepen our knowledge of the processes that govern planets, life, and the universe itself. Ceres reminds us that even in a region as seemingly barren as the asteroid belt, there are worlds of wonder waiting to be discovered. Its icy surface and hidden depths challenge our perceptions of habitability and our assumptions about where life might arise. In exploring Ceres, we take another step in humanity's journey to understand the cosmos and our place within it. Collisions and chaos. The violent dynamics of the asteroid belt. Imagine a region of space where ancient celestial bodies are constantly at risk of collision, their trajectories shaped by gravitational forces and random encounters. This is the asteroid belt, a zone of perpetual motion and latent chaos. While it may seem quiet from a distance, up close, the asteroid belt is a dynamic environment where collisions have played a central role in shaping its structure and revealing its secrets. What happens when asteroids collide? Unlike the fiery impacts we often imagine, most asteroid collisions occur at relatively low speeds compared to meteoroid impacts on planets. When two asteroids meet, the results can range from a gentle merging to a catastrophic breakup, depending on their relative velocities, sizes, and compositions. These collisions generate fragments of all sizes, from dust particles to larger debris that can become independent asteroids in their own right. Over millions of years, these events have continuously reshaped the asteroid belt, creating a complex web of trajectories and interactions. One of the most fascinating aspects of these collisions is their role in revealing the internal composition of asteroids. When an impact breaks apart an asteroid, it exposes the materials hidden beneath its surface. By studying these fragments, scientists can glean insights into the mineral and chemical makeup of asteroids, which in turn provides clues about the conditions in the early solar system. For example, meteorites that reach Earth often originate from such collisions, offering a tangible piece of the asteroid belt for analysis. The asteroid belt's chaotic environment is not entirely random. Its structure is shaped by the gravitational influence of nearby planets, particularly Jupiter. The gas giant's immense gravity creates regions of stability and instability within the belt, known as resonances. In these unstable zones, asteroids experience gravitational nudges that can alter their orbits significantly, often ejecting them from the belt altogether. Some of these ejected asteroids become near-Earth objects, NEOs, crossing Earth's orbit and occasionally posing a threat. Jupiter's gravitational influence also prevents the asteroid belt from coalescing into a planet. Periodic disruptions from the gas giant ensure that collisions remain a dominant force, keeping the belt fragmented and dynamic. This process, while destructive, is also creative in its own way, continually generating new asteroid families, groups of objects with similar orbits and compositions that can be traced back to a common parent body. The evidence of these collisions is etched into the surfaces of many asteroids, craters of all sizes that their landscapes, each one a testament to a past encounter. Some asteroids, like Vesta, bear scars from massive impacts that stripped away significant portions of their crust. These collisions can expose deep layers of material, offering a rare glimpse into the internal structure of these bodies. Vesta's Rhea Silvia Basin, for example, is one of the largest impact craters in the solar system, and its formation likely launched countless fragments into space. But collisions are not just destructive. They are also key to understanding the asteroid belt's history and evolution. By modeling these events, scientists can reconstruct the processes that shaped the belt over billions of years. Computer simulations allow researchers to track the trajectories of fragments, identify their origins, and even predict their future movements. These models also help refine our understanding of how planets and moons in the solar system formed, as the early stages of planetary growth involved countless collisions between smaller bodies. While most collisions occur within the asteroid belt, their effects can ripple outward. Fragments ejected from the belt can travel vast distances, influencing other regions of the solar system. Some may collide with planets or moons, while others become meteors that burn up in Earth's atmosphere. In rare cases, these fragments survive their fiery descent, landing on Earth as meteorites. These visitors from the asteroid belt have played a pivotal role in shaping our understanding of the cosmos, serving as natural messengers from space. In addition to their scientific importance, asteroid collisions hold practical implications for humanity's future in space. Understanding the dynamics of these events is crucial for designing spacecraft capable of navigating the asteroid belt safely. It also informs planetary defense strategies, as many near-Earth asteroids originate from the belt. By studying how collisions generate and alter asteroid trajectories, scientists can better predict and mitigate potential impacts on Earth. The chaotic environment of the asteroid belt also raises intriguing questions about the potential for life. Could collisions between asteroids and comets have delivered water and organic molecules to Earth, sparking the conditions necessary for life? Some theories suggest that such impacts played a crucial role in the early history of our planet, and similar processes may occur in other planetary systems. By studying the asteroid belt, we gain insights into the interplay between destruction and creation that shapes the universe. As we explore the asteroid belt, we are reminded that chaos is not the absence of order, but a different kind of order, one governed by the intricate dance of gravity and motion. Collisions may seem violent and random, but they are part of a larger pattern that has shaped the solar system for billions of years. They remind us that even in destruction, there is the potential for discovery and creation. Asteroid families and their origins. Within the sprawling expanse of the asteroid belt lies a hidden order, an intricate tapestry of relationships that connects seemingly disparate objects. These connections manifest as asteroid families, groups of asteroids that share similar orbital characteristics and compositions. They are the remnants of ancient collisions, fragments of a once unified body scattered across the belt. These families hold the key to unraveling the belt's history, offering a glimpse into its most cataclysmic events and the forces that shaped it. What defines an asteroid family? At first glance, the belt appears to be a chaotic collection of individual bodies, each following its own path around the Sun. However, by carefully analyzing their orbits, parameters such as semi-major axis, eccentricity, and inclination, astronomers have identified clusters of asteroids that move in similar trajectories. These orbital patterns suggest a shared origin, likely the result of a catastrophic collision that shattered a parent body into smaller pieces. The study of asteroid families begins with their identification. Using advanced computational tools and observational data, scientists map the positions and movements of thousands of asteroids. Patterns emerge as certain groups stand out, their similar velocities and paths pointing to a common ancestry. These families can range in size from a handful of members to hundreds or even thousands, depending on the scale of the original impact. One of the most well-known asteroid families is the Flora family, located in the inner region of the belt. Its members are predominantly S-type asteroids, rich in silicates and metals, which reflect the composition of their progenitor. The Flora family is thought to have formed relatively recently in astronomical terms, within the last billion years, making it a prime candidate for studying the processes that drive the evolution of asteroid families. Another prominent group is the Vesta family, which offers a unique window into the geology of its parent body. These asteroids are fragments of Vesta, one of the largest and most studied objects in the asteroid belt. The family was born from a massive collision that excavated the Rhea Silvia Basin on Vesta's surface, launching debris into space. By analyzing the mineral composition of Vesta family members, scientists have gained valuable insights into Vesta's internal structure and the processes that shaped it. Asteroid families also serve as natural laboratories for studying the effects of time and space. Over millions of years, the fragments of a family gradually disperse due to the combined influence of gravitational interactions and non-gravitational forces like the Yarkovsky effect. This effect, caused by the uneven heating of an asteroid's surface, can alter its orbit over time, leading to a slow but steady migration. By tracing these changes, scientists can estimate the age of a family and reconstruct the timeline of its formation. The study of asteroid families extends beyond the asteroid belt itself. Some families, or fragments thereof, are thought to be the source of near-Earth asteroids and meteorites. When collisions eject fragments from the belt, they can be propelled into orbits that cross Earth's path. These fragments provide a rare opportunity to study asteroid materials up close, offering clues about their composition, structure, and history. What can asteroid families tell us about the solar system's past? They serve as records of the belt's most dramatic events, preserving evidence of the collisions and disruptions that have shaped its evolution. By analyzing their compositions and orbits, scientists can infer the conditions that prevailed at different times and locations in the belt's history. For example, the presence of volatile-rich asteroids in certain families suggests that water and organic molecules were more widespread in the early solar system than previously thought. Asteroid families also provide insights into the processes of planetary formation. The parent bodies of these families were themselves formed through the gradual accumulation of smaller particles, a process that mirrors the early stages of planet formation. By studying the fragmentation and evolution of these bodies, we can better understand the forces that govern the growth and destruction of planetary precursors. Despite their importance, asteroid families remain an area of active research, with many mysteries yet to be solved. How do the initial conditions of a collision, such as speed, angle, and composition, affect the formation of a family? What role do external influences, like Jupiter's gravity, play in shaping their evolution? And how do the chemical and physical properties of family members vary over time? Answering these questions will require continued observations, advanced simulations, and, potentially, missions to study asteroid families up close. As we delve deeper into the asteroid belt's secrets, asteroid families emerge as a central piece of the puzzle. They are not merely groups of rocks. They are the remnants of ancient stories, fragments of worlds that almost were. By studying these families, we gain not only a deeper understanding of the asteroid belt, but also a clearer picture of the forces that have shaped the solar system. The role of Jupiter, guardian and disruptor. The asteroid belt's very existence, its structure, and even its chaotic nature are deeply intertwined with the influence of the solar system's largest planet, Jupiter. This gas giant, a colossal force of nature, plays a dual role in the story of the asteroid belt. It is both a guardian, protecting the inner planets from potential impacts, and a disruptor, preventing the formation of a planet within the belt itself. To understand the asteroid belt, one must first understand Jupiter's profound gravitational influence. Jupiter's immense mass, more than 300 times that of Earth, gives it a gravitational field strong enough to shape the orbits of countless celestial bodies, including asteroids. Early in the history of the solar system, this gravitational dominance had far-reaching consequences. As planetesimals in the region between Mars and Jupiter began to coalesce into larger bodies, Jupiter's gravity continually disrupted the process. The resulting instability made it impossible for these objects to grow into a full-fledged planet. Instead, the region became a graveyard of fragmented material, the birthplace of the asteroid belt. Jupiter's role as a disruptor is most evident in the orbital resonances it creates within the asteroid belt. Orbital resonances occur when the orbital period of an asteroid is a simple fraction of Jupiter's orbital period. For instance, an asteroid in a 3:1 resonance completes 3 orbits around the Sun for every 1 orbit of Jupiter. These resonances cause repeated gravitational tugs that amplify over time, destabilizing the asteroid's orbit and often ejecting it from the belt. The gaps in the asteroid belt's distribution, known as Kirkwood gaps, are a direct result of these resonances. These resonances are not just empty spaces. They are zones of chaos where asteroids are sent on new trajectories. Some are hurled outward into the outer solar system, while others are sent inward toward the inner planets. This mechanism explains why some near-Earth asteroids originate in the asteroid belt. It also highlights Jupiter's role as a conveyor of material, distributing fragments throughout the solar system. Yet, Jupiter is not merely a disruptor, it is also a guardian. Its massive gravity acts as a shield for the inner planets, including Earth, by deflecting or capturing comets and asteroids that might otherwise pose a threat. Many objects that stray too close to Jupiter are either absorbed into its atmosphere or slingshot into orbits that take them far from the inner solar system. This protective role has likely spared Earth from countless catastrophic impacts over billions of years, creating a more stable environment for the development of life. However, Jupiter's influence is not absolute. Some asteroids and comets still find their way past this guardian, occasionally resulting in impacts on Earth and other planets. In some cases, these impacts have had profound consequences. The asteroid believed to have caused the extinction of the dinosaurs, for example, was likely a fragment that evaded Jupiter's defenses. Such events remind us that Jupiter's role as a guardian is not infallible, and its influence is a double-edged sword. Beyond its direct effects on the asteroid belt, Jupiter's gravitational reach extends throughout the solar system, shaping the orbits of moons, comets, and even the other planets. Its migrations during the early solar system, as described by the Grand Tack hypothesis, may have played a pivotal role in the distribution of material that formed the asteroid belt. According to this theory, Jupiter initially migrated inward toward the Sun before reversing course and moving outward to its current position. This movement would have disrupted the protoplanetary disk, scattering material and contributing to the asteroid belt's fragmented nature. Jupiter's influence also extends to the Trojan asteroids, two large groups of asteroids that share its orbit around the Sun located in regions known as Lagrange points. These objects are gravitationally stable, trapped in a delicate balance between Jupiter's gravity and the Sun's. The Trojans are thought to be remnants of the early solar system, similar in composition to objects in the asteroid belt, and their study offers additional insights into the processes that shaped the solar system. As we study the asteroid belt, it becomes clear that Jupiter is both a sculptor and a sentinel. Its gravity shapes the orbits of asteroids, creates regions of stability and instability, and even influences the potential habitability of planets like Earth. Without Jupiter's presence, the solar system would look vastly different. The asteroid belt might have formed into a planet. The inner planets might have faced more frequent impacts, and the conditions for life on Earth might never have arisen. Jupiter's role in the story of the asteroid belt is a reminder of the intricate interplay between celestial bodies. It highlights the delicate balance of forces that govern the solar system, where a single planet can shape the fates of countless smaller objects. As we continue to explore the asteroid belt, Jupiter's influence looms large, a testament to the power and complexity of gravity in shaping the cosmos. Asteroids as time capsules, preserving the solar system's history. The asteroid belt, often viewed as a chaotic collection of rocky remnants, holds an extraordinary secret. Its asteroids are time capsules. These celestial bodies are fragments from the dawn of the solar system, frozen in time and space, preserving materials and information from over 4.6 billion years ago. By studying asteroids, we unlock a window into the earliest chapters of the solar system's history, gaining insights into how planets formed, evolved, and even how life may have begun. How do asteroids serve as time capsules? Unlike planets, which have undergone extensive geological and atmospheric changes, most asteroids have remained relatively unchanged since their formation. They lack tectonic activity, volcanic processes, and erosive forces that would otherwise alter their composition. This makes them pristine records of the conditions and materials present in the early protoplanetary disk, the swirling cloud of gas and dust from which the Sun and planets emerged. Asteroids are composed of the building blocks of planets, containing a mix of rock, metal, and in some cases, water and organic molecules. These materials were the raw ingredients of planetary formation, and their preservation in asteroids offers clues about the processes that shaped the solar system. For instance, carbonaceous chondrites, a type of meteorite originating from carbon-rich asteroids, contain complex organic compounds, including amino acids, which are the precursors to life. The discovery of such materials suggests that the chemistry of life was already underway in the early solar system. Asteroids also provide a record of the solar system's dynamic environment. Their surfaces are marked by craters and fractures, evidence of countless collisions over billions of years. These impacts preserve a chronological record of asteroid belt activity, from its violent beginnings to its more stable present. By analyzing these features, scientists can reconstruct the timeline of major events, such as the migration of giant planets or the late heavy bombardment, a period of intense asteroid impacts that reshaped the inner planets. One of the most compelling aspects of asteroids as time capsules is their ability to preserve volatile compounds, such as water. Many asteroids, particularly those in the outer regions of the belt, contain significant amounts of water ice. This water likely originated in the colder, outer reaches of the protoplanetary disk, where temperatures allowed ice to form and persist. The presence of water in these asteroids supports the theory that they may have played a role in delivering water to Earth and other terrestrial planets, creating the conditions necessary for life. Studying these ancient objects also sheds light on the origins of planetary differentiation, the process by which planets and large asteroids develop distinct layers, such as a core, mantle, and crust. Some asteroids, like Vesta, show evidence of differentiation, suggesting they were once molten and underwent processes similar to those that formed the rocky planets. By examining such asteroids, scientists can better understand the thermal and chemical evolution of planetary bodies. The tools for unlocking the secrets of these time capsules are as varied as the asteroids themselves. Ground-based telescopes, spacecraft missions, and laboratory analysis of meteorites all contribute to our understanding. Recent missions like NASA's OSIRIS-Rx and Japan's Hayabusa 2 have brought asteroid samples back to Earth, allowing scientists to study their compositions with unprecedented precision. These missions have confirmed the presence of complex organics, water-rich minerals, and rare isotopes, deepening our understanding of the early solar system. Asteroids also offer clues about the processes that continue to shape the solar system today. The Yarkovsky effect, for example, demonstrates how sunlight can alter an asteroid's orbit over time by causing uneven heating and radiation of energy. This effect, along with gravitational interactions, contributes to the slow but constant reshaping of the asteroid belt, ensuring that it remains a dynamic and evolving system. What does the study of asteroids reveal about our place in the universe? These ancient objects remind us that the materials and processes that created Earth and its life are not unique. The same chemistry, physics, and dynamics occur throughout the cosmos, offering a sense of connection to other planetary systems. By understanding the history of our own solar system, we gain insights into the formation of countless others, as well as the potential for life beyond Earth. Asteroids also serve as a reminder of the interconnectedness of all celestial bodies. The fragments that make up the asteroid belt were once part of larger objects, some of which collided, fragmented, and contributed material to other planets and moons. This cosmic recycling process continues to this day, linking the fates of asteroids, planets, and even life itself. As we delve deeper into the secrets of the asteroid belt, these time capsules challenge us to think about the past and future in new ways. They offer a glimpse into the solar system's earliest moments, providing a context for understanding the present and imagining what lies ahead. By studying asteroids, we not only uncover the story of our origins, but also prepare for humanity's next steps into the cosmos. Threats to Earth, near-Earth asteroids, and planetary defense. The asteroid belt may seem like a distant and isolated region, but its influence extends far beyond its boundaries. Occasionally, asteroids escape the belt, becoming near-Earth asteroids, NEAs, that orbit close to our planet. While most NEAs pose no immediate danger, a small fraction have the potential to collide with Earth, raising questions about the risks they pose and the strategies we can employ to defend against them. What transforms an asteroid from a distant, benign object into a potential Earth-crossing threat? The answer lies in gravitational interactions and the chaotic dynamics of the solar system. Jupiter's immense gravity often destabilizes asteroids within the belt, nudging them into new orbits. Some of these trajectories bring them into resonances with the inner planets, including Earth. Additionally, the Yarkovsky effect, a subtle force caused by the uneven heating and cooling of an asteroid's surface, can gradually shift an asteroid's orbit over millions of years, potentially placing it on a collision course with Earth. Near-Earth asteroids are classified based on their orbits relative to Earth. Those that pass within 1.3 astronomical units, AU, of the Sun are considered NEAs, while a smaller subset, called potentially hazardous asteroids, PHAs, come within 5 cents and are large enough, typically over 140 meters in diameter, to cause significant damage if they impact, while smaller asteroids, less than 25 meters wide, tend to burn up in Earth's atmosphere. Larger ones can have catastrophic consequences, depending on their size, composition, and impact location. One of the most well-documented examples of an asteroid impact is the Chicxulub event, which occurred 66 million years ago. A massive asteroid, estimated to be about 10 kilometers in diameter, struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs, triggering global wildfires, tsunamis, and a nuclear winter effect that led to the extinction of the dinosaurs and many other species. While such large impacts are rare, smaller events, like the 1908 Tunguska explosion in Siberia or the 2013 Chelyabinsk meteor in Russia, remind us that Earth is not immune to asteroid collisions. How prepared are we to detect and mitigate these threats? The first step in planetary defense is identifying and tracking NEAs. Over the past few decades, astronomers have conducted extensive surveys using ground-based telescopes and space missions. Programs like NASA's Near-Earth Object Observations, NEO, and ESA's Space Safety Program have cataloged thousands of NEAs, providing crucial data about their sizes, orbits, and trajectories. Despite these efforts, it is estimated that only about 40% of NEAs larger than 140 meters have been identified, leaving many potential threats undiscovered. Once an asteroid is identified as a potential hazard, scientists use advanced modeling to predict its trajectory and assess the likelihood of impact. These predictions rely on precise measurements and account for factors like gravitational influences and the Yarkovsky effect. If an asteroid is found to pose a significant risk, the next step is to develop a mitigation strategy. What options do we have for deflecting or disrupting an asteroid on a collision course with Earth? Several methods have been proposed, ranging from the use of kinetic impactors to the deployment of gravitational tractors. Kinetic impactors involve crashing a spacecraft into the asteroid at high speed, altering its velocity and trajectory. NASA's DART, Double Asteroid Redirection Test, mission successfully demonstrated this technique in 2022 by impacting the moonlet of asteroid Didymos, showcasing the potential for asteroid deflection. Gravitational tractors, on the other hand, involve positioning a spacecraft near an asteroid to exert a small but steady gravitational pull, gradually altering its orbit. This method is more precise, but requires significant time and resources. Another concept involves the use of nuclear explosives, either to deflect or fragment the asteroid. While this approach is often dramatized in movies, it is considered a last resort due to the risks of creating multiple fragments that could still pose a threat. For smaller asteroids, non-invasive methods like laser ablation or solar sails have been suggested. These techniques involve altering the asteroid's surface properties to change its orbit through the controlled release of material or by leveraging solar radiation pressure. While these methods are still in experimental stages, they represent promising avenues for future planetary defense efforts. The challenges of planetary defense extend beyond technology. International cooperation is essential, as asteroid impacts are a global threat that transcends national borders. Organizations like the United Nations have begun to address this issue, establishing frameworks for coordination and response. The International Asteroid Warning Network, IWN, and the Space Mission Planning Advisory Group, SMPAG, are key examples of collaborative efforts to share data, develop strategies, and prepare for potential impacts. Despite these advances, the risks posed by NEAs cannot be entirely eliminated. Smaller asteroids, which are harder to detect and track, can still cause localized devastation if they impact populated areas. Public awareness and preparedness are therefore crucial components of planetary defense. Educating communities about the nature of asteroid threats and the measures in place to address them helps build resilience and reduce panic in the event of an impact warning. As we look to the future, the study and mitigation of NEAs remind us of the interconnectedness of the solar system. The same forces that shaped the asteroid belt and delivered vital materials to Earth also create the potential for catastrophic impacts. By understanding and addressing these threats, we not only protect our planet, but also deepen our knowledge of the dynamic and ever-evolving cosmos. Exploration of the belt. Past and future missions. The asteroid belt, with its rich history and untapped resources, has long fascinated scientists and explorers. While its remoteness and vastness present significant challenges, a series of groundbreaking missions has begun to unlock its secrets, paving the way for future exploration. From the pioneering discoveries of past missions to the ambitious plans on the horizon, humanity's journey into the asteroid belt is a testament to our relentless curiosity and ingenuity. The first major milestone in exploring the asteroid belt came in 1991, when NASA's Galileo spacecraft became the first to encounter an asteroid up close. On its way to Jupiter, Galileo passed by Gaspra, capturing detailed images of its irregular surface. 2 years later, it flew by another asteroid, Ida, revealing the presence of a small moon, Dactyl, the first discovery of a moon orbiting an asteroid. These encounters provided the first glimpses of these enigmatic objects and hinted at the complexity of the asteroid belt. In the decades that followed, dedicated asteroid missions began to take shape. NASA's Near-Earth Asteroid Rendezvous (NEAR) Shoemaker mission, launched in 1996, was the first spacecraft designed specifically to study an asteroid. It orbited and eventually landed on Eros, providing unprecedented data about the asteroid's composition, structure, and surface features. NEAR Shoemaker's success demonstrated the feasibility of close-up exploration and set the stage for more ambitious missions. One of the most significant breakthroughs came with NASA's Dawn mission, launched in 2007. Dawn was tasked with exploring the two largest objects in the asteroid belt, Vesta and Ceres. By using ion propulsion, a revolutionary technology that allowed it to orbit multiple targets, Dawn delivered detailed insights into these contrasting worlds. At Vesta, the spacecraft revealed a surface scarred by massive impacts, exposing layers of material that hinted at its differentiation, a process more commonly associated with planets. When Dawn arrived at Ceres, it discovered mysterious bright spots, later identified as deposits of sodium carbonate, suggesting the presence of subsurface water and geologic activity. These findings fundamentally altered our understanding of the asteroid belt, highlighting its diversity and dynamic nature. Japan's Hayabusa missions also made significant contributions to asteroid exploration. The first Hayabusa mission, launched in 2003, successfully returned samples from the near-Earth asteroid Itokawa, despite numerous technical challenges. Its successor, Hayabusa 2, launched in 2014, targeted the asteroid Ryugu, deploying small landers and rovers to explore its surface. The mission returned a wealth of data and samples, providing insights into the organic and water-rich materials that may have seeded life on Earth. NASA's OSIRIS-RX mission, launched in 2016, continued this trend of sample return missions. After arriving at the asteroid Bennu, OSIRIS-RX mapped its surface in exquisite detail, uncovering evidence of water-bearing minerals and organic molecules. The spacecraft collected samples and is set to return them to Earth, offering a treasure trove of material for analysis. These missions have demonstrated the value of direct interaction with asteroids, allowing scientists to study their composition and properties in unprecedented detail. Future missions promise to push the boundaries of asteroid exploration even further. NASA's Lucy mission, launched in 2021, is on a journey to study the Trojan asteroids, two groups of ancient bodies that share Jupiter's orbit. These objects are thought to represent the building blocks of the outer planets, offering a glimpse into the solar system's early history. Lucy's multi-target approach will provide comparative data on a diverse array of asteroids, enriching our understanding of their origins and evolution. Another exciting endeavor is the European Space Agency's ESA Hera mission, part of an international collaboration with NASA's DART mission. Hera will study the aftermath of DART's impact with the asteroid Didymos and its moonlet, Dimorphos, assessing the effectiveness of kinetic impactors as a planetary defense strategy. By combining data from both missions, scientists will gain valuable insights into asteroid dynamics and the feasibility of deflection techniques. As technology advances, even more ambitious missions are being proposed. Concepts like robotic mining probes, asteroid rendezvous stations, and even crewed missions to the asteroid belt are being explored. These missions aim to not only deepen our scientific understanding, but also lay the groundwork for the practical use of asteroid resources, such as water and metals, in future space exploration. The exploration of the asteroid belt also raises profound questions about the ethics and governance of space activities. Who decides how and when asteroid resources are used? How do we balance scientific discovery with commercial interests? These questions will need to be addressed as humanity ventures further into the asteroid belt and beyond. As we look to the future, the asteroid belt stands as a symbol of humanity's capacity for exploration and discovery. It is a region filled with challenges, from its vast distances to the unpredictable dynamics of its objects. Yet, it is also a place of immense potential, offering answers to questions about the origins of the solar system, the possibilities for life beyond Earth, and the resources that could sustain our expansion into space. Each mission to the asteroid belt brings us closer to understanding not only this enigmatic region, but also our place in the cosmos. By exploring its depths, we reaffirm our commitment to curiosity and innovation, venturing ever further into the unknown. Water in the asteroid belt. The hidden reservoirs. The asteroid belt is often imagined as a dry, barren expanse, populated by rocky fragments that have remained unchanged for billions of years. Yet, hidden among its countless asteroids is evidence of water, a discovery that has fundamentally reshaped our understanding of this region. The presence of water in the asteroid belt raises profound questions about its origins, its distribution, and its role in the history of the solar system. Could these hidden reservoirs hold clues to the delivery of water to Earth and the potential for life beyond our planet? Water in the asteroid belt is primarily found in two forms: ice and hydrated minerals. Hydrated minerals are particularly abundant in carbonaceous asteroids, which are rich in carbon and other volatiles. These minerals form when water interacts with rock, leaving a chemical signature that persists even in the absence of liquid water. By studying the spectral fingerprints of these asteroids, scientists have identified widespread evidence of hydration, suggesting that water played a significant role in their history. One of the most compelling discoveries of water in the asteroid belt came with the exploration of Ceres, the largest object in the region. NASA's Dawn mission revealed that Ceres possesses a thin atmosphere of water vapor, likely produced by sublimation, when ice transforms directly into vapor. Dawn's instruments also detected bright spots in craters, composed of sodium carbonate and other salts, indicating the presence of briny liquid reservoirs beneath the surface. These findings suggest that Ceres may harbor a subsurface ocean, raising tantalizing possibilities about habitability. Ceres is not alone in its watery potential. Several other asteroids, such as 24 Themis and 65 Cybele, have been found to contain surface ice. Observations from telescopes and spacecraft have detected the spectral signature of water ice on these bodies, challenging the assumption that water could not survive in the harsh conditions of the asteroid belt. The survival of ice on these asteroids suggests that some regions of the belt are cold enough to preserve water, protected by insulating layers of dust and regolith. How did water come to exist in the asteroid belt? The answer lies in the origins of the solar system. During the formation of the protoplanetary disk, water existed as ice beyond the snow line, a boundary where temperatures were low enough for volatiles to condense. Many of the asteroids in the outer belt likely formed in this region, incorporating ice and other volatile compounds into their structure. Over time, some of these bodies migrated inward, bringing their water-rich materials closer to the Sun. The presence of water in the asteroid belt has profound implications for understanding the early solar system. It suggests that water was more widespread than previously thought, extending beyond the traditional boundaries of the snow line. This discovery also supports the theory that asteroids and comets may have played a crucial role in delivering water to the terrestrial planets, including Earth. By studying the isotopic composition of water in meteorites, fragments of asteroids that have fallen to Earth, scientists have found a close match to Earth's own water, reinforcing the idea of a shared origin. Water in the asteroid belt also holds potential for the future of space exploration. If humanity aims to establish a sustainable presence in space, water will be an essential resource, not only for life support but also for fuel production. By extracting water from asteroids, it could be split into hydrogen and oxygen, providing rocket fuel for missions deeper into the solar system. This concept, known as in situ resource utilization, ISRU, could transform the asteroid belt into a fueling station for interplanetary travel. However, the extraction and use of water from the asteroid belt presents significant challenges. Locating water-rich asteroids, developing technologies to extract and process water in space, and establishing legal and ethical frameworks for resource use are all hurdles that must be overcome. International cooperation and careful planning will be essential to ensure that these resources are used responsibly and sustainably. The discovery of water in the asteroid belt also raises intriguing questions about the potential for life. While most asteroids lack the conditions necessary for life as we know it, the possibility of subsurface oceans on bodies like Ceres introduces the idea that microbial life could exist in these hidden reservoirs. Studying these environments could provide valuable insights into the conditions that foster life and the potential for habitable worlds elsewhere in the universe. As we continue to explore the asteroid belt, water emerges as a central theme, a thread that connects the past, present, and future. It links the story of the solar system's formation to the origins of life on Earth and the possibilities for human expansion into space. By understanding the distribution and history of water in the asteroid belt, we take another step toward unraveling the mysteries of our cosmic neighborhood. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.